Okay, hello, welcome back. This is nuclear physics part 2. It's a nuclear reaction involving neutron. Is what we are going to see today together. So, the learning outcome of this lesson. After this lesson, you will be able to explain nuclear reaction energy and explain the Q value, and also distinguish the neutron interactions and understand fission and fusion, and also you will be able to explain nuclear cross sections. So let's start by a quick review of why nuclear reaction release energy. The mass of the nucleus is less than the sum of its constituent nuclei, as we have seen in a previous lesson, and this mass difference is called mass defect, and this mass defect is converted to binding energy, which is the energy that holds the nucleus together and powers nuclear reaction. And this binding energy will be equals to mass defect times c square, or speed of light square. So the nuclear reaction energy comes from the mass defect, or the change in mass from initial before the reaction to final after the nuclear reaction, that we are going to see about nuclear reaction. So what is nuclear reaction? Is the process where bombarding a nucleus with energetic particle alters its core structure and identity, which means you have a particle A and bombard it towards the nucleus X, and after the event you will get another nucleus Y and another particle which is B. So in the compact form, the nuclear reaction can be written as X in the brackets A comma B of Y, where X and Y are the nucleus before and after the interaction respectively, and A and B also a particle before and after the event respectively. So the energy of nuclear reactions comes from the change in the mass before the event and after the event, which means the reaction energy, or T value, is the total kinetic energy released or absorbed during a nuclear reaction, and it is equals to mass of X plus mass of A minus mass of Y minus mass of B times c square, where the term in the bracket is difference in mass. So the difference in mass arises from nuclear reaction we have seen earlier, and this Q value tell us about the nature of the reaction. If the Q value is greater than 0, the reaction is called exergic reaction, and in this case the nuclear mass is lost and directly converted to kinetic energy. And if the Q value is less than 0, the reaction is called endoergic reaction. In this case, the nuclear mass is gained, which means the reaction absorbs kinetic energy of the incoming particles. So that in this case, we need A particle is minimum kinetic energy to undergo such kind of reaction. So when we come to the interaction of neutron with matter, as we know, neutrons are a neutral particle, so it can travel certain distance before interacting with matter. So this interaction of neutron with matter can be categorized into four primary types in this lecture. So this is based on how they affect the target nucleus. The first one is elastic scattering. Second one is inelastic scattering. The third one is radiative capture, and the fourth one is induced fusion. And also there are others, but we do not include in this lecture. We will see in the future episode of nuclear physics lecture series. Okay, let's see elastic scattering, where the upcoming or neutron and outgoing neutrons are remain the same. So it is donated by n comma n, or such kind of scattering can be equivalent to the collision of hard spheres, like a billiard ball in classical physics. So in this last scattering, total kinetic energy will be conserved, which means the upcoming neutron with high kinetic energy hit the target nucleus. Then the change in kinetic energy of the neutron will lead us to the recoiling of the nucleus. So the change in kinetic energy of the neutron will be equals to the change in the kinetic energy of the recoil of the nucleus. As you are observing from this video, the Q value will be 0. Okay, in elastic scattering, in this type of scattering, kinetic energy is not conserved, which means high neutron interact with the target nucleus and absorb some the target nucleus absorbs some kinetic energy of the neutron and become excited. Then the neutron is slowed down. The scattered neutron will be slowed down. Then the excited nucleus release energy or release gamma. So we can see the energy excitation of energy in the target nucleus, and it absorbs some kinetic energy of the neutron. So kinetic energy is always less than zero in this kind of reaction. Okay, when we come to radiative capture, which is donated by n comma gamma, in this case, neutron captured by a nucleus, then the reaction changes atomic number of the nucleus. The atomic number of nucleus changes by some factor, which means there is maybe increasing of number of nucleons. Look at the video here. In this case, there is emission of gamma radiation after the capture of this neutron, which means after emission of the neutron, it will become excited, more energetic, and to be more stable, it will release gamma radiation. Okay, the last one, and the very important one is induced fission, which is represented by n, f, where the first indicates a particle, projectile particle, and the last one will be indicates the product or after the reaction. So in this case, a neutron absorbed by a target nucleus. Just look at the video. The first neutron absorbed by a nucleus like uranium 235, then forms another fissionable nucleus like uranium 236. Then there will be a release of new neutrons. Another neutrons will be released from this excited fissionable nuclei after the absorption of a neutron. So the neutron before the event and after the events are different. So this induced fission has some unique property, which is it may release extremely high amount of energy. Also, it may release different type of radiations and release neutrons, a number of neutrons, and production of radioactive fission product will be also observed in this kind of induced fission reaction. Okay, in turn, a nuclear reaction, neutron released in fission produce an additional fission in at least one further process. As you are observing from this diagram, the first neutron hits uranium 235 and this uranium 235 will release another fission neutron, sorry, and other fission fragments, and this process repeats itself, and this process may be controlled or uncontrolled. The controlled one is in the nuclear power, where uncontrolled one will be in the nuclear weapon. Okay, it is very important to see also about nuclear fusion. Nuclear fusion is when two or more nuclei combine to form one or more different nuclei. Since the fusion reaction produce uncharged neutron, it is very important to see the topic here. For example, in the fusion reaction, when deuterium and tritium combine together to form most stable nuclei of helium and free neutron, which means both deuterium and tritium combined together at very strong or critical temperature and to form helium and neutron. That means deuterium with one proton and one neutron, and the tritium with one proton and two neutron combine to form the most stable helium and neutron, free neutron, by and they will give energy as well. It is very important when we talk about nuclear reaction, we should have to consider nuclear cross section also. Nuclear cross section is a measure of the probability that a specific nuclear reaction will occur between a incident particle like neutron or a projectile particle and a target nucleus. And we can see this nuclear cross section in two categories: microscopic and macroscopic. Microscopic nuclear cross-section is the effective target area. Single nucleus present to incoming neutrons, which means it is the area of interaction seen by the neutron, and its unit is Barn, which is 1 barn is equals to 10 raised to minus 24 centimeter square. So that means it's the probability of single nuclear reaction occur with a neutron and target nucleus. Whereas microscopic is it is the total target area presented by all the nuclei in a bulk volume, and it represents the probability of the reaction occur per units distance traveled as a particle moves through the material, which means its unit is in per centimeter. So, for example, if we say the microscopic nuclear cross section of some neutron is, let's say, 0.8 per centimeter, this means neutron has 80% chance of reacting for every centimeter it travels. So it's all about our today's lesson. If you have any question regarding my video presentation, please don't hesitate to fill the form, ask any question, or provide me a feedback. Thank you very much. Have a nice time. Enjoy the